Good afternoon friends. Today we discuss with GTU question paper January 2012. In last question we have stopped with the series impedance. In series RLC circuit, impedance is given by three cases. We have already discussed about the case number 1 when the XL is greater than XC, means when inductive reactance is greater than capacitive reactance. When inductive reactance is greater than capacitive reactance, at that time VL voltage is greater than VC, means inductive voltage is greater than VC. At that time impedance is given by under root R square plus XL minus XC square. Now let's go with case number 2 when inductive reactance is less than capacitive reactance. That means capacitive reactance is more than inductive reactance and circuit becomes capacitive. So when reactance of capacitance is more, it obvious in that case the capacitive voltage is more than inductive voltage. So VC is greater than VL. So now in that case the resultant voltage is given by VC minus VL. So resultant is VC minus VL. Same as the previous case, we go with the equation V square equal to VR square plus VC minus VL square. Obviously capacitive voltage is large, so we subtract from capacitive voltage minus inductive voltage. So now put the value of V. Value of VR is I R square plus value of VC is I into XC and VL is I into XL bracket raised to square. Now taking I as a common, so I square Z square equal to I square R square plus XL minus XC minus XL square. From these two brackets I have taken out I as a common. When I take I common, there is a square. Now I square and I square both are cancel out, so remaining term is Z square is equal to R square plus XC minus XL square. Now we get the value of impedance, so we take the square root on both sides, so Z equal to under root of R square plus XC minus XL square. So case 2 when the capacitive reactance is more than inductive reactance, impedance is given by R square plus XC minus XL square whole square root. And now we go with case number 3. It may happen that both reactants are same, so XL is equal to XC. Inductive reactance is equal to the capacitive reactance. In that case the voltage of inductor and voltage of capacitor both becomes equal, so VL equal to VC, so the resultant voltage becomes 0. That is the important point in our circuit. When both are equal, inductive reactance and capacitive reactance, the resultant between them is 0, because if we take VL minus VC or VC minus VL, both voltage are same, then difference is 0. So V equal to VR, only resistive voltage drop is given, so V equal to VR. Now put V equal to IZ and VR equal to IR. Now both side I cancel, so we get equation Z equal to R, and that is the minimum impedance in case when XL is equal to XC. So in totality we get the value of impedance in this three case in series RLC circuit. Impedance Z is given by under root of R square plus XL difference XC square, because no matter if XL is large or XC is large, we take the difference and then we take the square. So values may be negative or positive, we go for the square, then it becomes positive. So overall impedance equation is given by R square plus XL minus XC square in a 3 condition: when XL is greater than XC, when XL is greater than XC, or XL is less than XC, or XL equal to XC. So from these 3 equations we get the value of our impedance. Okay, for 3 mark, 4 mark it is here. Now question number 5a, very important question. Compare the magnetic circuit and electric circuit, stating the similarities and the difference between these two. Now we compare our magnetic circuit and the electric circuit. So here first we discuss about the similarities. Okay, now the left part show the electrical circuit parameter and the right part show the magnetic circuit parameter. In that electric circuit parameter, here first point in the similarities, the closed path for the electric current is called an electric circuit, and for the closed path for the magnetic flux is called the magnetic circuit. As we know that in electric circuit current is flowing, while in magnetic circuit when current flow through the circuit, flux is produced. That means magnetic flux is induced into the magnetic circuit. So electric circuit, there is a closed path for the electric current, and for the magnetic circuit there is a closed path for the flux. Now second point, current flow through the conductor while unit is ampere, and here flux is produced in the material and unit is Weber. See, this is the important point. Current is flowing through the circuit while flux is producing. That's why it's produced into the material. Flux never flow. Remember, flux never flow. It only produce and remains or alter. Okay, third point, electromotive force EMF is necessary to force current to flow in electric circuit, and the unit is volt. To flow current in electric circuit we required a EMF, while a magnetic motive force MMF is necessary to produce flux in the material, and unit is ampere into turn. So here MMF, that means magnetomotive force, is required to producing a flux in magnetic material. Fourth similarity, important point, property of material to oppose the flow of current is called resistance, and unit is ohm. Now one property of any conducting material or any electrical circuit is it opposes the flow of electric current into the circuit, and that is known as resistance. Unit is ohm. While the property of material to oppose the establishment of magnetic flux is called reluctance. So unit is ampere turn per Weber. So in magnetic material there is some property which opposes the establishment of flux, and that is known as reluctance. So in similarities, here resistance, in the point 4 there is a reluctance, unit ohm and unit ampere turn per Weber. So resistance is given by rho L upon A, while L upon sigma A, that is rho is conductivity, conductance, and sigma is conductivity. Similarly, reluctance is also given by the equation L upon mu R, where L is length of magnetic material, while mu is represented by mu 0, mu R, and A is cross sectional area of magnetic material. So we compare the equation of resistance and reluctance. Similarly, one term is conductance, which is known as 1 upon resistance. That means inverse of resistance is known as conductance. So similarly, the inverse of reluctance is known as permeance. There is a resistivity of material and there is a reluctivity of material. Point 7 is important. Material in electric circuit having some resistivity, while material in magnetic circuit having some reluctivity. So the same point we can define conductivity is inverse of resistivity, and similarly permeability is inverse of reluctivity. So both are the comparable term, conductivity and permeability, reverse of resistivity and reluctivity. And as we know that last but important point is current. Current is EMF upon resistance, while flux is MMF upon reluctance. Remember, this is the important equation. We will use it further in the derivation or in a formula of to find out the current and find out the flux. The flux or current can be find out using this term, and both are the similar term. Current is flowing in the circuit, flux is producing in the circuit. EMF is electromotive force, MMF is magnetomotive force. Resistance oppose the current, reluctance oppose the establishment of flux. Now 10th point, current density. Current density is represented by the delta equal to L upon A, that means area per meter square, and flux density is given by B equal to phi upon A, flux per area, Weber per meter square. And last, electric field intensity. Electric field intensity always define the voltage per meter. So electric field intensity capital E is defined by E is equal to V by D, volt per meter. And similarly magnetic field intensity in the form of that it is a strength of field, how electric field and how magnetic field. Then intensity is defined H equal to Ni upon L, Ni upon L, length of magnetic material. So Ni ampere into turn upon meter. So there is 11 points of similarity between the electric circuit and magnetic circuit, while there is a few dissimilarities between, or we can say differences between electric and magnetic circuit. So let's discuss what are the dissimilarities between these two circuits. First point, electric current actually flow in electric circuit due to the flow of electron, while flux does not actually flow in the magnetic circuit. As I told you in the first point, the flux is always produced in circuit, magnetic circuit, it does not flow. So one dissimilarity is current is flowing from one point to other point, while flux is not flowing from one point to other point. Second, resistance of conductor remains constant if the temperature not change. In a circuit, if temperature is not changing, of room temperature is not changing, it remains constant, then there is no change in any resistance value. But in reluctance of a magnetic circuit is not constant and it depends upon the flux density. If flux density is large, then reluctance is large. Okay, if flux density is less, then reluctance is less. So reluctance it depends on flux density, it does not remain constant. Third point, there is constant expenditure of energy to keep the current flowing in electric circuit, while constant expenditure of energy, that means we require electromotive force to flowing the current. We constantly provide the supply, then and then current will be flow. If we switch off the supply, then current will not flow. While in the point of magnetic circuit, energy is required to establish the flux and not to maintain it. Once flux has established, then we have to don't worry, it will remain as it is, so we do not need to maintain it. There are many number of electric insulators like plastic, mica, rubber, all are the insulators for the electric circuit in which the current or does not passes. So these all are the known as insulators, but there is no perfect magnetic insulator. even in air the magnetic flux is producing. So there is no any perfect magnetic insulators in magnetic circuit. The 4 points of dissimilarities between electric circuit and magnetic circuit. Okay, now explain the effect of temperature on three materials: conducting material, insulating material and semiconductor material. Okay, question is very short for a 3 mark. So we study in deep what is conducting material, insulating material and semiconductor material, and what is the effect of temperature on it. So first we go with the energy band diagram of the three material. See, the first is energy band diagram of insulator, second is energy band diagram of semiconductor, and third is the energy band diagram of conductor. What represent? The blue part is conduction band, yellow part is forbidden gap, and orange part is valence band. There is a three band: valence band, forbidden gap and conduction band. In valence band always electrons are there. When electrons are go from valence band to the conduction band, then and then current is flowing. So in insulating material, as shown in the figure, forbidden gap is large. In semiconductor material, forbidden band gap is very small in some electron volt, but in conductor there is no forbidden gap. That means there is conduction band and valence bands are overlapping. There is no any forbidden gap. That means electrons are easily passed from valence band to conduction band because there is no forbidden gap. Let's understand by individually. What is the effect of temperature on the insulator? See the energy band diagram. Now at high temperature, some electron can go from the valence band to the conduction band and can constitute a very small electric current. At a very high temperature, some electron can go because there is a forbidden gap is very large, up to 5 to 8